everyone, today I will be discussing the relationship between cross-sectional area and mass flux. To begin, let's describe the concept of diffusion. Diffusion involves the movement of molecules from a high concentration to a low concentration. Take a look at this video. The dye is diffusing out into the water to areas where there is no dye. We see here that the concentration gradient is our driving force for this mass diffusion. Diffusion can be classified into a variety of different types. The first type of mass diffusion is metallic diffusion. Metallic diffusion occurs when the atoms of one type of metal diffuse into another type. This type of diffusion is typically seen in alloys and is also referred to as impurity diffusion. Metallic diffusion can take on two forms, vacancy and interstitial. Vacancy diffusion involves the metal atom moving into an empty spot in the lattice. Interstitial diffusion refers to an atom being able to diffuse between the atoms of another metal. Another type of diffusion is mass transfer through semipermeable membranes. This type of diffusion is seen in cell membranes where molecules can travel in and out of a cell, and in osmosis, which refers to the movement of water. The simplest model for diffusion is Fick's first law of steady-state diffusion. Here, mass flux is equal to the mass flow rate per unit area, where the cross-sectional area is normal to the direction of diffusion. Mass flux is also inversely proportional to cross-sectional area. Now that we've established a great background context on diffusion, let's move into my experimental design. My experiment examines the inverse correlation between mass flux and cross-sectional area through the observation of how smaller gelatin cubes facilitate greater mass flux when immersed in warm water. The materials required for this experiment include gelatin, food dye, warm water, ruler, and a stopwatch. The experimental procedure followed was preparing the gelatin as per cooking instructions and adding dye prior to cooling. Once the gelatin was cooled, I cut the gelatin into cubes of varying sizes and recorded the cross-sectional area of each. Then I warmed a cup of water and submerged the gelatin cube in the warm water and recorded the time it took for the dye to diffuse out. This is an overview of my experimental setup, where I have 5 gelatin cubes of varying sizes and recorded the cross-sectional area. Cube 1 had a cross-sectional area of 13.75 centimeters squared with a total diffusion time of 7 minutes and 2 seconds. Cube 2 had a cross-sectional area of 10 centimeters squared and a diffusion time of 4 minutes. Cube 3 had a cross-sectional area of 7.5 centimeters squared and a total diffusion time of 2 minutes and 10 seconds. Cube 4 had a cross-sectional area of 5 centimeters squared and a diffusion time of 1 minute and 40 seconds. And finally, Cube 5 had a cross-sectional area of 2.5 centimeters squared and a diffusion time of 40 seconds. Assuming the concentration of dye per block remained constant, from the data I observed, the smaller the cross-sectional area became, the faster the rate of dye diffusion per minute per area occurred, validating the inverse relationship of mass flux and cross-sectional area, and thus supporting my hypothesis. Additionally, we can also observe the directly proportionate relationship between mass transfer of dye and cross-sectional area, especially in the larger sized cubes. In the 5.5 centimeter sized cube, the rate of mass transfer became slower as the gelatin cube dissolved in water. As the gelatin began to dissolve, the area of mass transfer decreased and the molecules became more closely packed, making it more difficult for the dye to readily diffuse out. While this experiment focused on studying one-dimensional mass transfer, it is important to note that multi-dimensional dye transfer is occurring and that other experimental factors such as the temperature of the water can also impact the total mass flux, as the diffusivity of the dye through the gelatin in the water is also a function of temperature. Diffusion through semi-permeable membranes is a very important process in the optimization of drug delivery systems of soft gel capsules. One of the simplest ways mass diffusion of pharmaceuticals can be modeled is by Fick's first law of steady-state diffusion. Fick's law models the passive diffusion through semi-permeable membranes. Passive diffusion allows a drug molecule to move from the area of high drug concentration inside the capsule to the body through the gelatin matrix. To ensure the active pharmaceutical ingredient can readily diffuse to the body, drug developers must consider the size and shape of the soft gel capsule. In the experiment, we saw that the cross-sectional area is inversely proportional to the mass flux. To create an extended release pharmaceutical, drug manufacturers could reduce the cross-sectional area of the outer gelatin matrix. Finally, here are my references. Thank you for listening.